Okay, now show that, or at least we will relate these one parameter Lie groups of transformations to the notion of curves in n dimensions. Recall that if you have a one parameter Lie group of transformation, then the map G star, G on star on some vector x giving you some vector x bar is essentially what we had before. So that, for example, we said that the parameter G, which comes from a one parameter Lie group of transformation, or rather Lie group, one parameter Lie group R plus, and it acts on a vector xy, for example, and then x bar would be something like x over 1 minus your parameter gx, y over 1 minus your parameter gx. And we showed that this, for example, is a one parameter Lie group of transformations because it satisfies certain properties. So what's essentially happening is you've got your Lie group and it has elements like G, your identity, etc. The identity on some point on your manifold is left unchanged. And so this is your manifold, which in this example would be R2, but we're looking at a general case. So what happens is a Gx on some point on the manifold gives you a new point on the manifold, x bar, say. And then you might take another value, you might take an H from the set, and when that x on x bar, it may give you another point, x double bar, etc. So what's happening is, as the parameters, as the elements of this Lie group G acts on the elements of the manifold, it transforms from one point on the manifold to another point. As another one acts onto it, you get another point, etc., etc. And notice that on this manifold M, what's happening is you're getting a point being transformed, 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 and you're tracing a curve on this manifold. And this manifold could be R2, R3, R4, whatever. And you recall from way back that a curve in 2 dimensions can be expressed in Cartesian form or in parametric forms. But in R2, R3 rather, R4, R5, etc., a curve can only be expressed in parametric form. So that, if you recall, that if you have a map phi that maps an interval to, say, Rm, and this interval is a subset of the real line, then this would amount to a phi acting on t, say. So t is your real value, phi acts on t, and it gives you a vector in Rm. So this will be, for example, phi 1, and phi 1 will be a function of t. Phi 2, function of t, and this will have m coordinates because this is a point in m dimensions. So here you would have, for example, phi m of t, m coordinates there. And what happens is you end up with, for various values of t, you have points that are being plotted in Rm. And eventually what you're getting is a curve in Rm. And that's your parametric curve. Now you may also recall that at each point, the tangent to these curves are written as phi dot. So the tangents to this curve in Rm are what we'll call phi dot. That's dot is derivative with respect to the parameter t. So you differentiate each coordinate phi 1 dot, etc. until you get phi m dot. So for a specific value of t, phi of t will give you a point. Phi dot at that value of t would give you the tangent at that point. Now, because of the discrepancy between this notation, you've got a point that's written in coordinate form. You've got the tangent vectors that are written in coordinate form. We will rewrite from now on the tangents in a different notation in which we use this, what is the partial derivative notation. So we will write the tangents in an alternative form in the following way. So the first coordinate of this tangent, for example, phi 1 dot, will be the coefficient of d by dx1. So this will be phi 1 dot plus the second coordinate, phi 2 dot, will be the coefficient of d by dx2. So this will be phi 2 dot, etc. And this will be done for each of the components of the tangents. So in fact then, this is an alternative representation of that, the tangent vector. So now we know this would represent the tangents, that would represent the point on this curve in Rm. Right, so that here's an example, I suppose. Suppose you have an example where your phi of t is given by, say, 2 cosine t, 2 sine t, and let's suppose the third coordinate is t. So that this is a curve that is going to be in R3. Your x coordinate is 2 cos t, your y coordinate is 2 sine t, and your z coordinate very simply is t. So the question is, what is this curve in R3? Well, in the xy coordinate you've got 2 cos t, 2 sine t, so that's a circle of radius 2. So in planes parallel to the xy coordinate you've got circles of radius 2. So as you increase in t, the x and y coordinates form a circle, but as you increase t, the z coordinate just goes up. So what's happening is you've got these circles forming in xy, but the z is being pulled up. So what you're ending up with is a helix. Right? So at any point, say on the helix, you'd have a tangent, right? And the tangent is for a specific t value given by phi dot. So in this case it will be minus 2 sine t, 2 cos t, 1. So that's the tangents at various values of t. Or we just said that the tangents will be written as minus 2 sine t, t by dx, plus 2 cosine t, d by dy, plus 1 times d by dz. So x1 is x, x2 is y, x3 is z. So, but in this case, we could actually rewrite this in terms of x, y, and z, because you notice x is 2 cos t, y is 2 sine t. So this is minus y d by dx plus x d by dy plus 1 d by dz. So this is the set of tangent vectors for the helix that we just sketched. So you can write the tangent vectors in that form or in this form. This form of representing the tangent vectors is what I'm going to refer to as the vector field notation of the tangent vectors. Now, going back to the one parameter Lie groups of transformations. The one parameter Lie groups of transformations essentially are forming curves, are tracing curves on your manifold M. So if you take G, that's your parameter like your T. It's acting on a point, say XY. Let's restrict it to 2 coordinates. It's giving you a point X bar, Y bar. This is in 2 coordinates. So what's happening here is your Lie group is your real line with 0 as the identity. Your manifold is very simply R2. So what's happening is if little gx on the point xy, there's the point xy, call it vector x, it's being transformed to a point x bar. And if another parameter hx on x bar, you get x double bar, say a new point, etc. And you notice what's forming is this curve. Okay? And this curve, of course, is a curve on the manifold M, which is in R2. And this curve then has a parametric form, and the parametric form is given by that. So, for example, when gx on that example xy, giving you, say, g cos x minus, or rather, sorry, got it wrong. It was x cosine g minus y sine g. So this is x bar, and y bar was then x sine g plus y cos g. So this is in fact your x bar, y bar, your new point on the manifold. So what's happening is you've got your manifold. Your manifold is a subset of R2. You've got this point xy. There is xy. And when your parameter gx on this, you're getting a new point x bar, y bar. So it's being transformed to that. And when another parameter x on x bar, y bar, you're getting a third point, etc., etc. And it is this curve. Where are we? It is this curve that's being traced, and this curve has a parametric equation given by that. And we can determine the tangent at each point. We just differentiate the first coordinate with respect to the parameter g, the second coordinate with respect to the parameter g, etc., etc. So every one parameter Lie group of transformation like that is tracing a curve. And this curve is in Rm, in this case R2. These curves in R2, the equation of the curves are that, have tangents. As so for each value of the parameter, they have tangents. So this, there are tangents at each point. For example, there's a tangent there. At this point, there's a tangent there. And these tangents are given by the derivative of x bar, y bar with respect to the parameter g. So you differentiate the first coordinate with respect to the parameter, like we were differentiating with respect to t previously. You differentiate the second coordinate with respect to the parameter g, you get these tangents for specific values. And I mentioned that we will write the tangent vectors in terms of, or rather with this alternative notation called the vector field notation. So it turns out that every one parameter Lie group of transformation of this type here, whose equation is essentially that, is a curve, and the tangent to the curve can be written in vector field form. So let's sum it up. If, in general, if G star vector x, which is x1, x2, x3, etc., or xy or xyz, is equal to x bar, and let me just remind you, here's an example of that type. Then the tangent vectors, if that there is, I should say, if this there is a one parameter Lie group of transformations, then the tangent vectors, or the tangents, can be written in vector field form, can be represented not necessarily in coordinate form, but with this alternative representation, can be represented as vector fields. As I mentioned, these tangent vectors have these alternative notations, and let's say those vector fields, so the first coordinate of that tangent vector will be the coefficient of d by dx1, the second coordinate d by dx2, etc., etc. And then the last coordinate, if this is an m-dimensional manifold, will be the coefficient of d by dxm. And there's a way of determining, a simple way, it's just a matter of differentiating each of these coefficients, where, for example, the coefficient of d by dx1 will be the derivative of the first coordinate of the one parameter Lie group of transformation with respect to the parameter. So at each of these cases, let's give these things a name. With this, for example, let's give it a name. Let's call this xi1, let's call this xi2, and this xim. So where, for example, xi1 will be the derivative of x1 bar with respect to the parameter. xi2 will be the derivative of x2 bar with respect to the parameter, etc. until xim is the derivative of, it's ordinary derivative of xm bar with respect to g, but we have the added property that since this is not any old curve, it's a curve that is a one parameter Lie group of transformations, so we can actually, because at g equal to 0, when the parameter equal to 0, the point does not change, so evaluate this at g equal to 0, each of these things. I suppose I should do an example of a known one parameter Lie group of transformation. So example says find the tangents. When we find the tangents, we're going to find it in vector field form of the one parameter Lie group of transformation given by, let's do an example that we've seen before. The parameter was g. This was, I think, the first example we dealt with, or similar to the first example, where the point xy is transformed to x bar y bar, and the x bar is x e to the g, y e to the 2g. So that we showed as our first example was a one parameter Lie group of transformations. Now let's take the derivative of the first coordinate. I'm not calling it x1, I'm calling it x. Differentiate the first coordinate with respect to the parameter and then evaluate that at equal to 0. So if you differentiate the first coordinate, which is that coordinate x bar, with respect to g, you get x e to the g, and put g equal to 0. This is equal to x. Then if you differentiate y bar, that is y bar, and the derivative of y bar, which I called x2 previously, with respect to the parameter g at g equal to 0 is equal to, first do the differentiation. If you differentiate with respect to g, you get y, differentiate e to the 2g, you get 2e to the 2g, and evaluate that at g equal to 0. This is then 2y. So this will be the coordinate of d by dx, that will be the coordinate of d by dy. Therefore, the tangent vectors are given by x d by dx plus 2y d by dy. So these are the tangent vectors in vector field form corresponding to the one parameter Lie group of transformations. So let me sum it up. This is the one parameter Lie group of transformation, which is g star of xy. First coordinate I'm calling x bar, second y bar. This would be the first coordinate in the tangent vectors. That would be the second coordinate in the tangent vectors. And hence we get this representing the tangent vectors in vector field form. Here's an exercise. Show that the, oh, okay, I should rather say, instead of saying show, I'll say find. Find the vector field which are going to represent the tangent vectors of the one parameter Lie group of transformation given by g star acting on xy. Again, I'm using xy instead of x1, x2. The first coordinate is x bar, the second coordinate is y bar, where x bar is x cosine g minus y sine g, x sine g, let me write that properly, this is sine of g plus y cosine g. You do exactly what we did before. So this is essentially how we write every one parameter Lie group of transformations tangent vectors in the vector field form. What we do next is the reverse, and that is that suppose I give you the tangent vectors. How do we reconstruct the one parameter Lie group of transformations, that is the curves, from these given tangent vectors? So now you're given the tangent vectors. So essentially, conversely, let's say conversely, I give you tangent vectors. Okay, I'm giving you the profile, and I'm saying reconstruct the curve for which these form the tangent vector, or the curves, the family of curves for which these are the tangent vectors. But not only that, that the curves would represent one parameter Lie groups of transformations. Okay, so I'm going to do this essentially by way of example. So this is merely a procedure rather than proving how this is done. And it's all built into the fact that we are dealing with reconstructing one parameter Lie groups of transformations. So I'm saying here, finally, conversely, given vector fields are tangents, right? Find the one parameter Lie group of transformations. So you are given the tangents, those are the tangents, you are reconstructing the curves for which these are the tangent vectors. Okay, let's clear the page up nicely. Okay, so let's do this by way of example. And let me just remind you, this is all built into the definition of one parameter Lie groups of transformations. So consider the vector field, and let's take a simple one now. And let's give this vector field a name. Let's say the vector field, so these are the tangent vectors now, are given by x d by dx minus 3y d by dy. And this is how we reconstruct the one parameter Lie group of transformations. We're looking for x bar and y bar. So we use the bar coordinates. So first of all, we let dx bar by dg, you see the one parameter Lie group coming in here, equal x bar, that's this x9 bar coordinates, and dy bar by dg equals minus 3y bar. So let me just say what this is. If you bar that x, you get x bar. You bar the minus 3y, you get minus 3y bar. But because this is a one parameter Lie group of transformations, we know that when g equals 0, x bar equals x. This was condition 2 in the one parameter Lie group of transformations. And y bar equals y. This is when g equals 0, when you're using the identity. So we need to solve these two differential equations. Put that in a slightly different color. This differential equation, that differential equation, subject to this initial condition. Right, and this example is rather straightforward. Let's start with the first one. So if we take that, it's a variable separable straightforward. You get dx bar over x bar equals dg. You integrate both sides. You get the ln of x bar equals g plus, let's write the integration constant as ln of k. Therefore, x bar equals, by exponentiation, e to the right hand side, so that gives us k times e to the g. Now, when g equals 0, x bar equals x, y bar equals y. We don't need the y bar in this case. Okay, so impose this condition in there. The x, when you put g equal to 0, the x bar becomes x. This is k, and this is e to the 0. So it's clear that this gives us the solution, or at least a form of k. So therefore k equals x, and therefore we have x bar sorted out as x e to the g. That's the first case. From the second case, which is dy bar by dg equals minus 3y bar, we can do again a variable separable thing. We get dy bar over y bar equals minus 3 dg. integrate both sides, we get therefore the ln of y bar equals, if you integrate this, you get minus 3g plus, let's call this constant ln of c. And therefore, by exponentiation, y bar equals c e to the minus 3g. Put g equals 0 where y bar equals y. If there was an x bar, you put an x bar equal to y, x also, to get what? When g equals 0, the y bar becomes y, and this becomes e to the 0, which gives us that c is equal to y. Thus, substituting back, we get therefore y bar equals c is now y e to the minus 3g, putting this into there. So therefore x bar, y bar is, what was x bar? X bar was x e to the g, x e to the g, and y bar from here at the bottom is e to the y e to the minus 3g. And of course this was g star xy. And this is then the one parameter Lie group of transformation reconstructed from its given vector field up here. This was the vector field. An interesting example would be, I guess you can try this, examples. One, I should say here, find x bar, y bar, i.e. find the one parameter Lie group of transformations given the vector field. In the first case, let's suppose the vector field is x squared d by dx minus xy d by dy. Secondly, suppose the vector field, the tangent vectors are y d by dx minus x d by dy. These are familiar examples we've seen before, but here I give you the vector fields, you construct g star xy. And you can do this for 3 dimensions also. Here's a simpler one, but one similar to the example I've just done. So here's x d by dx plus 2y d by dy minus z d by dz. So here's one of 3 coordinates. This number 3 is very similar to the example I've done above.